Okay, so the next speaker is Tudor Dimofte, who's going to talk about 3D mirror symmetry and conflict homology.
Thanks. So this talk is going to have three different parts. First, I want to review a few general aspects of CQFT in 3 dimensions, hopefully connecting with what happened last week and things that happened earlier this week. Then I want to talk about a particular class, or in fact 2 classes, of CQFTs in 3 dimensions that come from topological twists of 3D n equals 4 gauge theories. These various aspects of these twists have been studied before. In sigma models, the B twist was, in fact, in gauge theory, the B twist was first written down by Blau and Thompson many years ago, and then in sigma models, it was studied by Rozansky and Witten, and Kapustin, Rozansky, and Salina tried to give a definition of this 2 category that Alexei mentions in his talk. On the A side, relatively little has been done, in part because it's very hard. At the top level, or on closed 3 manifolds, particular 3D n equals 4 gauge theories, abelian ones, end up giving you Seibert-Witten invariance. This A twist is a reduction of the Donaldson-Witten twist from 4 dimensions. So there's a bit that's been studied there from a completely different angle. But as far as categorical structures, Kivinen has said some things about pure gauge theory, and the affine construction of Coulomb branches really sits inside an A-twisted 3D n equals 4 gauge theory. Sits inside that TQFT. And I'll try to explain one perspective of how. And then, if there's any time left, I want to talk about a particularly cool application of these ideas. So, as Alexei said 2 days ago, his construction with Lev-Rozansky of HOMFLY-PT homology from matrix factorizations sort of, well, I think he sort of said this. It involves this this KRS2 category and sits firmly in a B topological twist of 3D n equals 4 gauge theory. I mean, he didn't say the words 3D n equals 4 gauge theory, but I will. And I think using what we know now, we can build an A-twisted mirror of basically all of the ingredients in Alexei's talk.
I just confirm that all of the smart stuff is all for physics in my talk. I did, KRS is the key to the construction.
Yeah. So, I mean, you should take with an asterisk the statement that we can construct an A-side mirror to everything. Lots of things are still hard, and in fact, this not homology example and the fact that we sort of know what to shoot for has been teaching us a lot of lessons about what things on the A side should look like. Okay. Also, I should mention, so aspects of this are joint work with Nick Garner, my grad student, and Mike Gerasi, who's a postdoc at Caltech, at Davis. Sorry. Justin Hilburn and Phil Yu on the math side, and everything about homology is also joined with Alexei and Lev. Right, and more things that I want to say now. The homology story is closely related to just about every other appearance of not homology that has come in physics. So it's there's a direct relation with string theory and M-theory realizations, and the 3D setups that I'm going to talk about can be obtained by starting from surface operators in 4D Yang-Mills, the sort that Gukov and Witten studied, and reducing those on a circle. There are lots of connections to many things. Also, the 3D n equals 4 theories that I'm talking about here are really sitting on the boundaries of 4-dimensional n equals 4 theories, and these twists in 3D are what happens on the boundary of A and B twists related to geometric Langlands in 4D. Okay, but let me actually start with the talk. So TQFT in 3 dimensions has at what I think of as the 0-dimensional level, has an algebra of local operators. This is an E3 algebra. This talk is going to be called OPS. The picture is that these sort of points in 3-dimensional space, dually, they are the thing that the TQFT assigns to a 2-sphere that surrounds one of those points. We will only be interested in the cohomology. So this, in twisted theories, comes about as a DG object. In cohomology, this is a graded Poisson algebra with an even Poisson bracket. It's the usual sort of Poisson bracket. And it can be quantized by turning on what in physics one calls omega backgrounds, and in math it involves working equivariantly with respect to a U1 rotation, literally for the entire E3 operad. The E3 operad has to do with homology of a configuration space of points or balls, and one can turn on U1 equivariance there.
What is the degree of this Poisson bracket?
It's degree 2. Minus 2. Okay. Also, in physics, one talks about a moduli space of vacua. There's a notion of this in TQFT that, at least I learned from David Ben-Zvi, not sure whom to attribute it to, but in TQFT terms, what physicists call moduli space of vacua is spec, or rather functions on. Affinization of that is local ops. In dimension 1, extended operators of dimension 1, one has what physicists call line operators. And so there's a thing called lines, which is it's an E2 monoidal category, i.e. graded tensor. The objects of lines are literally lines in 3-dimensional space. The tensor product comes from collision. And there is a distinguished object which is the trivial or empty line. It's the identity for the tensor product. It's the unit. For the tensor product. Now, Hom in this category computes local operators sitting at a junction of two lines. So if I have L1 and L2, can ask about the vector space of local operators sitting at the junction, and that by definition is Hom.
So these are all vertical lines?
All the structure is local. So no, they don't all have to be vertical lines.
But when you say that they collide, they never collide like this? It would always...
They could certainly collide the way you are describing, but then I would describe. I mean, so if I had something like this, I would say the theory is topological. So let's put them like that and like this, and think of whatever happens there as an endomorphism of the tensor product here to the tensor product, or as a Hom from the tensor product here to the tensor product there.
So could we think about, in reference to John Fast's talk, that you're sort of saying what sort of local stratifications you want to allow, and to do that you just need to specify data for sort of generic things, and then you're going to have some universal way to do this on a general level.
Yes.
So you might imagine that this is some kind of factorization homology.
I believe so, and I say yes with great confidence, but all the things I actually work with in computer are relatively simple at the level of applying factorization homology. But totally, I think that is exactly the idea. This is very local structure that we then want to include in arbitrary configurations. In terms of this thing called the moduli space, which appears in physics talks all the time, the expectation is that the category of lines is sheaves on M. In particular, the trivial line, endomorphisms of the trivial line are just local operators sitting in empty space. So N1 is ops, and 1 should be thought of as the structure sheaf.
So coherent sheaf, yes?
Yes. I mean, in the B-twist, it will literally be coherent sheaves. But I think it depends what sort of functions we're talking about. Yeah.
A question. You said that this will be E2 monoidal, but sheaves is infinity.
And is that rather the algebra, like the category of modules, or the algebra of like modules of an E3 algebra is an E2 category?
Yes.
But this could be richer, right?
Again?
This could be richer. Line operators not necessarily generated by the trivial line.
Yeah, I know that.
Yes, sorry, absolutely. And that will actually come up when I write down what the categories of lines are. Yes.
So I think Sam wants to say that there's a category in which you're computing endomorphisms of its distinguished object, and that is more commutative than the structure on the categorical.
But this is only on cohomology. This M is cohomology. So maybe it's symmetric on cohomology, but not bifurcating.
I would love to gain a deeper understanding of all this by the end of the talk.
So I think, or maybe what you expect is that this is like the classical case, and in your quantum case, you expect to get some kind of deformation of that, which is no longer commutative. And
Oh,
in fact
sorry,
goes
no,
into-
and you do. And,
Yeah.
right.
Yeah,
Sorry,
I'm
you do.
just
No, yes, but
responding
but
for you.
there's
He wants
a
to continue.
dictionary.
He
Right.
already hinted he wants to continue.
Absolutely, yes.
Mhm.
Okay. Right. And finally, in dimension 2, I'm going to consider boundary conditions. In general, one has interfaces. So there's a 2 category. There's a 2 category whose objects are ways to cut space-time off. And you might want it to be an E1 category because the E's go down. And interfaces is an E1 category, but boundary conditions is just boundary conditions is just a 2 category. Hum between 2 boundary conditions. I have B1 and B2 in some order. Hum in this 2 category consists of line-like things at an interface of B1 and B2. Hum or end of a particular B is a monoidal 1 category. So end of a particular B is lines going between B and itself. It's monoidal because they can collide. It's not braided because they can't move past each other. And finally, there are some interesting relations between 1 and 2. In particular, between lines in the bulk and boundary conditions. And there are 2 that I will actually try to use later. And so one of these was invoked by Alexei. In fact, both of them were. So for a fixed boundary condition, there's always a map that sends lines in the bulk to lines on the boundary. So that's this map. If we have a line in the bulk, we can collide it with the boundary and get an endomorphism of B. The image is in the center of this monoidal category. If I have a line in the bulk and some other line on the boundary, I can take the bulk line and put it on one side or the other, and it doesn't actually matter precisely because I can lift it back into the bulk. So in fact, the map is to the center of that. And if the boundary condition is big enough, in particular if it generates the 2 category of boundary conditions, you expect that thing to be an isomorphism. So if B is a generator, then bulk lines should actually be the derived center, the Drinfeld center, or the Hochschild homology of this monoidal category.
Cohomology or cohomology?
Homology? Derived center? Cohomology? Yeah. Sorry. Yes.
What do you mean by generator? Or maybe that's a homework problem.
That's yeah. So I know an example is what I mean by generator, and I'm not sure. I know all the right axioms and things to say about two categories to actually say what I mean by generator.
But you expect that these two categories will often have a single generator?
Well, I want to say that if they don't, then I can just take direct sums. I think I can take direct sums.
No, but I
The
meant
boundary conditions. Okay. So yes, in examples of theories I've actually played with, there is a generator. Physically it's a single, simple, well-defined thing, and this works. In particular, it worked in Lexi's talk, and I'm not sure that was perfectly clear.
Maybe one way that you could mean generator is that you have this B, and then you can act on it by your E3 algebra, and then you can ask if that HOMs with any other element in your boundary 2 category, and then a statement like this is sort of.
Yeah. The other way I would say big enough is that there's another boundary condition that inverts it up to something up to something trivial that factorizes off. So if there's a situation like this where there's some other B, so going from theory to empty to theory itself, such that a deformation of this configuration is the trivial interface, then this has to work.
But is the definition to say that B is generating if home from B to any B prime is not 0?
Yeah, I mean that's what I would want to say. But
Huh?
that is what I want to say. I'm afraid
B
that
prime
it's too
is not
naive,
0.
but that's exactly.
Right. So you could make a definition like that in which it only relies on the underlying one category of the 2 category, which is what you were saying, or you might ask for generator to make reference to the 2 category structure. And so I guess that was my question in some sense.
Yeah, and I'm not sure I see the difference well enough to distinguish.
So the existence of a B check like that actually puts some size constraints on B. Like, B can't be too big for sort of a statement like just holding the nose. You might just have like an inclusion or something.
Sure.
So I worry since the modulus is a vacuum might not be affine. There just might not be a sort of
except there are.
Well, good thing he said if.
Sorry, I am going to just postpone this discussion because I think there are potentially more interesting things to say, or at least things I can say with more confidence. So
could I ask one question about the inclusion of lines into the boundary?
yeah.
So if you say these 2 lines that you've drawn there, the white and the orange one, that you want that they commute,
Yes.
but then within B I still can't move one of them past the other.
Well, but you can always lift that. So if precisely when you have one of these lines that came from something in the bulk, within B you can lift it off and then collide it onto the other side.
But so wouldn't the commutation have to happen in this boundary?
Sure. So I'm saying as far as end boundary B goes, I'm saying there's an isomorphism in the sense of braided monoidal categories between whatever. 0 between L0 tensor L and L tensor L0.
You're saying I is a braided tensor functor by obvious.
It is exactly this.
Yeah, this is for the central functor.
Yeah, central functor. Thank you.
Yes. Cool. Final picture that I'll draw is that a cyclic. The cylinder picture. If we have a cyclic collection of boundary conditions, with line operators, with interfaces between them, this should define an object in the bulk line category. And in fact, defines, and I will say how. In lines in the bulk, and so here I was thinking about the cylinder being closed on the inside. I can invert this entire picture, and just in terms of pictures, why you would expect this to happen, is that if we invert everything and get a thin cylinder like this with something empty on the inside and the 3D theory on the outside, this looks like a line. And then one can pull this picture apart and say exactly what are the HOMs between this and every other line. HOM I don't know what to call this object. Maybe volt B. So HOM in the category of bulk lines between B and the identity comes from looking at local operators at a cap. So this entire configuration caps off, and then there's a vector space of local operators there, and that's supposed to be the HOM. In physics speak, one would say this is the Hilbert space of, that's one definition, or it's the Hilbert space.
Is it, so you have some functors and you take composition and then you take the trace of this composition? Is that what,
absolutely,
what you do?
yes, and that's the same.
And it takes values in the trace category?
Yes.
Which turns out to be equivalent to the center?
Which is lines.
Which is equivalent to the center in this case?
Yes.
I mean, it's not always, but in this case it will be.
So there's center and co-center, and people were bugging you about that earlier. In good cases, they coincide as categories, and it sounds like Pablo expects that your case is like that.
These pictures are oriented. In order to have a field theory, those things have to be the same.
Yeah.
They're the same in mythology.
Yeah, well, in any case, then you will get a trace will lie in the center.
Yes, yeah, totally. And with any other, so you can throw any other L in there, any other bulk line, which just means some bulk line in, we're just talking about that HOM, and you actually compute things by going halfway, by folding this out until the boundary becomes a plane, and it looks like this. And if there's an L, you can bring that to the boundary as well. And then it's literally some HOM in the boundary category that computes that. Okay. Right. So 3D equals 4 theories in 3. Sorry. So I should say, like, the reason I even tried to explain all of this with a lot of help from the audience is because this is the sort of structure I would like to find in A and B twists of 3D n equals 4 gauge theories. And I am coming from the physics side and trying to ask, like, what are all these various pieces of structure, and how can I actually compute them and do something useful with them? So what are 3D n equals 4 gauge theories? So they're labeled, the ones I want to consider are Constantine's case of polarizable matter. So they're labeled by a, it almost pains me to say this, a complex reductive group, because in physics it would obviously be a unitary group, compact thing. But this is a math talk. This is a complex reductive.
This is a safe space.
And
you can make it more painful and say connected complex reductive. I'm not actually sure I want to. So there's a group and there's a symplectic representation. Finite dimensional symplectic representation that's polarized like that. There's a more general class of things where this is replaced with an algebraic symplectic space, or in physics a hyperkähler manifold. And if the group is trivial and you have a hyperkähler manifold here, that's what leads to sigma models and Rozansky-Witten theory and KRS2 categories. The gauge theory case, I think, is interesting and often resolves sigma models in a way I'll explain. In a way I'll explain now. So if you ask what the target of this theory is, the best answer from a mathematical perspective seems to be the symplectic quotient in a derived sense.
The symplectic quotient, or the actual sort of like a stacky version?
The stacky version of that. Sorry. So I mean a derived fiber of the moment map mod G. 3D n equals 4 theories have two branches in their moduli space. So there's a thing called a Higgs branch, which is this. And for purposes of this talk, it's going to stay derived. And there's a Coulomb branch. Which mathematically is given by the BFN construction. For what it's worth, structurally, the Coulomb branch always looks like a complex integral system over a base that's T mod W, whose generic fibers are dual complex tori. And this is generic. Now, other quick facts. Many gauge theories come in pairs. Many familiar classes of gauge theories come in pairs related by what's known as 3D mirror symmetry. For a suitable GNR, there is a G dual and R dual, and I should be very clear, these are not independent. You don't just dualize G and R independently. There's a dual pair. With, in particular, the property that Higgs and Coulomb branches are swapped.
Moreover, 3D gauge theories admit two topological twists. In other words, there are two ways to think of these as TQFTs, which we'll just call A and B twists. And if we're dealing with a theory that fits in a nice pair like that, the A and B twists get swapped. It's, in this sense, very much like two-dimensional mirror symmetry. And in fact, two-dimensional mirror symmetry happens on boundaries of these 3D theories. Or if we start taking HOMs between boundary conditions, we will get B model categories on one side and Fukai categories on the other side.
Now your question, if you start with a gauge theory on one side, would you always expect to get another gauge theory?
No. And so pairs like this are, in one sense, extremely special, but also linear quiver varieties are of this type. All abelian theories are of this type. So there are many examples that come up frequently in applications that fit in this sort of classification. On the other hand, if you just start with pure gauge theory, that does not have a gauge theory mirror. So in general, absolutely not.
When you say that 2D mirror symmetry happens at the boundary, you mean like at the boundary, the moduli spaces you get are literally like SYZ dual in the sense of homological mirror symmetry?
No. I mean a statement about how supercharges transform under the action of the mirror symmetry involution. And that if you say if you form a sandwich and trap a two-dimensional theory between two boundary conditions, these two-dimensional theories will be mirror symmetric. Whether they are sigma models or Mandel-Ginsburg models or whatever, it depends on how you describe these boundary conditions. But you will get a mirror symmetric pair.
In the sense of 2D homological mirror symmetry.
In the sense of 2D homological
so you
mirror
expect
symmetry.
them to be like
exactly.
SYZ vibrations and everything else.
And the associated categories are precisely the HOMs. The category of boundary conditions for the sandwich is HOM BB prime. And I'm saying this category had better be equivalent to the dual sandwich. And one of them is going to look B-like and one of them is going to look A-like.
You can be a bit more precise in special case, right? If you take toric varieties, for example, you actually do get to see the
that's true. Yes.
The horizontal mirror on the other side. Exactly.
Yeah.
So, yeah.
Yes. Okay. So, I want to tell you how a few pieces of the categorical structure in A and B twists. Local operators on the B side are just functions on the Higgs branch. Local operators on the A side. Local operators on the A side are given by the BFN construction, for example. They're functions on the Cohen branch. The part that I have been working on most involves these categories of line operators in the bulk. There are two approaches. So if we want to know what a category of lines is.
So a quick question. So you mentioned that mu inverse of 0 is going to be derived.
Yes.
So this means that opt B is a DG algebra?
Yes.
But what about ops A? It looks like it's an ordinary algebra for you.
It sort of does. In cases where the representation is faithful, if there's enough matter, then this is not a DG algebra. That's just an ordinary algebra.
If the moment map is flat.
And these are precisely when the map is flat. And these are precisely the cases that have gauge theory, that have a chance to have gauge theory mirrors. If I throw in pure gauge theory, the moment map is certainly not flat. There is a putative mirror of this, as in Konstantin's work, which is a sigma model onto this double N reduction. And I mean, this is not a gauge theory in the sense that I described, and is not reductive.
So this
This is a smooth space. And if we ask what is the Coulomb branch of the smooth space, you get a DG thing. It's in fact it's cohomology of that smooth finite dimensional space.
By C there, did you mean cohomology? C of the ocean.
But we are talking about this flat moment map case, so it doesn't matter.
Yes, I did. As far as line operators go, so the approach, no matter what one does, involves sort of compactifying on a circle surrounding the line. In TQFT, you would literally say the category of lines is what the TQFT assigns to the circle. Physically, the way one analyzes line operators is by looking at solutions to BPS equations, to looking at fixed points of some supersymmetry on the space of fields, solving some PDEs, and then trying to extract some sensible algebraic structure out of that so that you can actually compute something. There's another, so that is actually my perspective, and I could say a lot about that. Given the audience, there's another approach, which is an application of methods that that Chris Elliott and Phil Sang-Yu used to analyze geometric Langlands based on ideas of Costello. And there you start with a twist that's not topological, it's fully holomorphic, and impose an algebraic structure from the very beginning, and deform that to topological twists, either A or B. And so that is possible to apply here, and I'm just going to tell you the answer, which is going to look crazy, derived, and stacky. This Elliott-U type construction exists in derived algebraic geometry. The category of B-type lines is quasi-coherent sheaves on the derived loop space of R mod G. Sitting in here is a smaller thing. Taking the formal neighborhood of constant loops, one gets, or completing around the identity line, one ends up with what I would naively have thought was the category. In other words, coherent sheaves on the Higgs branch, and that's in perfect agreement with Kapustin-Rozansky Salina for sigma models. And one, so the identity here is the structure sheet. On the A side, lines A gets expressed as what you would want is D modules on the loop space of R modulo the loop group. On the B, qualitatively, if you try to solve these PDEs in the B-twist, you get constant fields, or covariantly constant things. You get flat connections and constant fields. And that localizes the theory to something finite dimensional, and you have a chance to get a category like this. In the A-twist, the solutions to PDEs look like solutions to monopole equations or Dirac equations. Those don't localize. Just like the A model in 2 dimensions, you get holomorphic maps. And so this has zero chance of being something finite dimensional. You get loopiness. And so the algebraic version of this is G of k a covariant demodulus on R of k, where k is formal is formal Laurent series, and O is formal Taylor series. The identity line is R of O mod G of O, and I was going to try to make that more precise and sensible and reasonable, but I'm sort of out of time, so ask me afterwards. A nice thing about the identity line in this formalism is that endomorphisms of the identity by a result of Kosin-Ginsburg lead you to the BFN construction. So this is for a more homology of the BFN space, which I will write like this. So BFN space is 2 copies of R of O and a copy of G of K, with a restriction that I call these elements xg and x prime. X prime is g times x. Mod G of O on both sides. Literally acting on this copy of R and that copy of R and on the 2 sides of G. That, I mean, it looks horrendous, but one can actually compute, and that is the definition of functions on the Coulomb branch that was given in math. As far as the 2 categories go, I'll say something very brief. Also, right, when, of course, when I compute the category of lines, I not get E modules, I get a Fukaya category on the loop space, which by some optimistic infinite dimensional generalization of Nadler-Zaslow should look like E modules on the face, which is what that is. Okay. And this is, so not everything is known here. A giant set of objects, I assume a generating set, especially given comments I made earlier, where I'm pretty sure the whole thing is just generated by a single boundary condition. So the objects look like algebraic vibrations over Lagrangians in the Higgs branch. And this is the sort of thing Alexei drew that expressed it with superpotentials, and I'm being super vague. So the objects are things like this, where the image is Lagrangian. So the simplest ones are literally Lagrangians in the Higgs branch, but they can be decorated. The HOMs in the B category are in the same, so there might be a larger thing sitting here that has to do with the derived path space, but at the same level that I simplified this category to coherent sheaves on the Higgs branch, this is sheaves on the fiber product. And that is very usefully broken apart in terms of matrix factorizations. In the A category, this a priori looks really horrendous. And the only description I can give is not actually an algebraic geometry, because the dimension gets too low to use something like algebraic D modules. Physics expectation is that this will be Fukaya. You would hope that it's a nice fiber product, but you don't localize to constant maps, so it is some sort of fiber product, but it's a fiber product like this, where you have to take paths, take maps from an interval into the Higgs branch, with the restriction that at the two ends of the interval, you land in the correct Lagrangians. And there's a superpotential, and there's a gauge group, and so this sort of looks like some equivariant Fukaya-Seidel category, infinite dimensions, and I feel a little bit embarrassed just saying that. There is a superpotential. The critical points of the superpotential are constant maps, but you can't, in a model world, you can't just localize to critical points. Okay. Right. So I think 5 minutes. Let me think a little bit about what to say. So first, an interesting part of our work in progress is figuring out in the not homology case what this category is, and there seems in that particular case to be a finite dimensional version of the right hand side, where because the boundary conditions are particularly nice, one can reduce this. Just to connect with Alexi's talk on the B side, this was some category of matrix factorizations, and we can try to find the mirror there, and we have a putative guess. Let me just write down what the theories are that are relevant for not homology. So for HOMFLY homology, and I'll just do the case of the bottom row. So for HOMFLY-PT at a degree 0, on the B side, G is GLN. The representation is an adjoint and a fundamental. And on the A side, in fact, it's exactly the same, because this theory ends up being self-mirror. So G check is also GLN, and R check is adjoint plus fundamental. And then there are boundary conditions. So the entire data of the braid is encoded in a boundary condition in one of these cylinder configurations. Which is why I had brought it up earlier. Apologize, I went too slowly. The braid gets encoded in this monoidal category of interfaces on the boundary. and as one goes around, there's a representation of the braid group in this category of interfaces. That means the thing we choose as the boundary condition is super important because that's basically where all the interesting braid is happening. So curly B on this side involves a fibration of T star flag over the Higgs branch here. And I should have really said the Higgs branch and the Coulomb branch in both cases look like singular versions of the Hilbert scheme. And we can resolve them to the Hilbert scheme of endpoints on C2. The boundary condition ends up being a particular fibration of D star of the flag manifold over super loose, but this is why T star flag came up in Alexi's talk. And then immediately what one gets from the general abstract stuff is that any boundary condition with a configuration of interfaces had better define for you a bulk line operator, in other words, a sheaf on the Hilbert scheme. So that map from cyclic configurations to line operators in the bulk is what lets you associate to the closure of a braid a sheaf on the Hilbert scheme. Homs between that sheaf and the identity line, or in other words, the Hilbert space in the cylinder, is the not homology. So here, so Homs in bulk lines between whatever this sheaf is and the identity line is HOMFLY homology. That is a vector space, and then what happens on the A side? So here the flag manifold, as one was going around, it was complexified Kähler parameters that are being braided. There are roughly n, it's n minus 1, complex Kähler moduli in this space that in algebraic geometry are never actually seen. But if you think of this as an actual hyperkähler manifold, they're Kähler moduli. And these braid transformations have to do with flops of various divisors in T star flag. On the A side, the dual boundary condition is incredibly simple, which is what makes this entire game fun and interesting. On the A side, the check is what I would call a Dirichlet boundary condition. It fixes. It just fixes if x is in GLN and I is in CN. This is half of T star. It fixes x to be a matrix with constant, with non-zero constant eigenvalues, and I to be just a constant vector. And so this is a Lagrangian in T star, and that gets symplectically reduced to a Lagrangian in the Higgs branch. This is super nice. One thing one can immediately do without saying anything about Fukaya categories is write down what object in the category of bulk lines corresponds to a braid. So given a braid, what happens is that the positions of the braid strands get encoded in these eigenvalues. These eigenvalues are the mirrors of the resolution parameters for flag. I will finish in a second. So the braid is encoded in an element, giving this a dependence as we go around the circle. One gets an element GLN of most generally of K, but if we want to encode a braid, we should use something, or if we want to actually be able to evaluate on the circle, we should use something like the round polynomials. And then doing a computation in this category of D modules on the loop space produces out of the data of the braid something that looks like a generalization of an affine Springer fiber over this point.
But this makes it immediately algebraic, not arbitrary braids are available probably.
Exactly. So this sort of this sort of thing will definitely be algebraic, and to move beyond that, we have to figure out what this is to get actual braid generators and produce an arbitrary braid. There's a one-step construction that works beautifully for algebraic braids, and one gets some. It's a slight generalization of the old story of Alexei with Eugene and Vivek Shende and Jake Rasmussen about cohomology of affine Springer fibers and not and HOMFLY homology. And so at the end of the day, with these algebraic knots, following one's nose through mirror symmetry and various categorical details, one arrives, for better or worse, at an old construction, but in a cool way. And stop. Thank you.
Okay, questions?
So am I right? So the braid does not actually appear as a physical braid in free space here.
No, it does the way Alexei drew things. So but that requires other dimensions and manipulations. In particular, it really requires going to higher dimensions and thinking about brains. But so strictly speaking, absolutely no. It appears just because there happens to be a representation of the braid group in endomorphisms of a particular boundary condition.
Okay. When you spelled out your algebra of line operators, your boundary categories, sort of everything you spelled out has a sort of natural Q deformation, Q analog, like
yes, you just take K theory, or
yes, I guess, but yeah, so K theory or quantum Hamilton reduction or quantum geometric. I guess my question is there a physics? What would correspond physically to this Q deformation?
So, then there are different. Sorry, there are different ones, and I don't want to touch quantum geometric language. But in one common place to look for Q deformations is by adding a circle. And so, for example, if you want K-theoretic Coulomb branches, you just fiber a circle over the entire theory. It's still effectively a 3D TQFT, but the
is there any sense in which this theory is where that circle is sort of contracted to a point?
Yeah.
Yeah, but those are two different. I mean, K-theoretic Coulomb branches is different than quantization. I mean, you were asking about Q analog.
Yeah, but this,
but I mean, the K-theoretic one also has a Q analog. I mean,
but
okay, you're right.
Sorry, I mean, there's also a quantization that. I mean, there are many. There's a quantization from a mega background that I understand well.
I would believe that the thing you said gives all of those different.
I see.
Yeah, so when you talked about this tensor category business, so if you take one B capital, which is something that lives in a two-dimensional thing, brain, then the other B's perhaps can be understood as modules of that B.
Sure.
So
I would. Sorry. I would want it.
So
I would want modules over the algebra of lines.
over the
category
modules.
of lines in the bulk.
So
You could.
no,
sorry,
no,
you could do what you're saying as well. Yes.
Endomorphisms of B is a tensor category.
Yeah,
you
yeah,
take
you can do
modules
that.
over that, and that would be all the possible.
Sorry, you
B
could
primes.
represent that way. Yes. Yes.
Or what you mean by a generator is that the functor from your category to that category of modules is fully faithful.
Exactly. I absolutely agree.
Well, yes, surjectives.
No, just fully faithful. I mean, if there was, he would be happy if there was only one B.
But all of the modules have to be present, right? No.
I mean, sorry. So what you're saying is you take any other B prime, and we're going to probe it with B by thinking of whatever happens at the interface between B and B prime as a module category for endomorphisms of B, right? Endomorphisms of B are like this; they act on that, and the point is this: you may miss some things. B prime and B may just not talk to each other. They're boundary conditions for which this may be.
Yeah, but if you have a generator, it will talk to everything.
But yeah.
No,
exactly.
but the question is, can it also happen that you're not going? So if you have a B, you have this category of endomorphisms of B. It's a tensor category. You can look at all its modules, which are nice enough. And are they all going to be present as boundary as these branes, or not necessarily?
You're asking, can you go backwards? And I think the answer is yes. By
well, you don't have
similar
to.
things.
You can always enlarge your theory to include those, but you don't have to.
Okay. So
it's some completion procedure that doesn't have any bad effects.
So you could have only parts of the B's.
Yeah, it's like in Noah's talk. There are these various choices in category theory. Well, then you have the same sorts of choices in two-category theory about what sorts of co-limits you give yourself and whether things need to be complete in various ways.
I think, sorry, saying it. I think in physics you often have similar choices.
Right. If you don't mind me making a comment, so this issue that's come up in your talk and Konstantin's talk about whether the moduli of vacua is affine or not is exactly an alpha versus beta issue in factorization homology. The alpha version of factorization homology is sort of supposed to be sufficient for implementing field theories with an affine moduli of vacua, but as soon as the moduli of vacua is non-affine, then that's sort of where you need the beta theory in some sense. And that's exactly the same kind of an issue about whether this object B generates. That's also an alpha versus beta issue. If you have a generator, then that means that's more like the alpha theory being sufficient versus when you don't, then you kind of need more of the beta theory.
Okay, so let's thank the speaker again. We start at 2:30 as scheduled.